This lecture we're going to be covering chapter 2.2 on the line spectra and the Balmer-Rydberg equation. So what is a spectrum? So a spectrum is a distribution of frequencies of light absorbed or emitted by an object. So I'm sure you've all seen a image of a prism before, where you have a single white light that enters the prism, and then it comes out split into its individual colors of light. So what we have here, if we think back to our last lecture, knowing that all light is actually different waves of electromagnetic radiation. And so the energy of each of those different photons of light is dependent on the wavelength and frequency of the specific light. And so as we talk about going from visible light from red all the way to violet, it's just changes in the wavelength and frequency of each of those different waves of light. And so when we see white light coming into our prism, this is actually a composition of many different types of wavelengths of light that compose all of the light within the visible spectrum. And then so the differing rates in which they flow through the prism is what separates them out into our individual rainbow sort of light. So if we look at light coming out of a white light bulb, the spectrum type is continuous, meaning that we have all different frequencies or wavelengths of light. So that would be light, say, coming off of like an incandescent light bulb. Whereas if you take a look at excitation of an element such as mercury vapor, you could see it would be composed of a few different wavelengths of light. For example, this image here, you can see that the excitation of mercury vapor gives us some blue light, some green light, and a little bit of yellow and red. Whereas you can have a laser, which is monochromatic, which can put out just individual wavelengths of light. For example, this red, green, and blue lasers. Okay, so each different light is defined by its wavelength or frequency. So as we excite different elements, so when energy is applied to an element through burning, electrical excitation, etc., they can emit discrete wavelengths of electromagnetic radiation called a line spectrum. So here are examples of line spectra that are released by the excitation of our first few elements that we see here on the periodic table. So we have hydrogen, helium, neon, lithium, calcium, sodium, strontium, potassium, and mercury. So you can see that there are very clear-cut individual wavelengths of light that are emitted by each of these different elements. And each element has its own diagnostic fingerprint, which defines itself as its own element. So no two elements have the exact same line spectra. So these are so instead of being continuous light, like from our white light bulb, the incandescent light bulb, when we excite these elements, we get these very specific wavelength patterns of the emitted light. So this is actually very important in setting the stage for our understanding of how the atom is actually composed. So what do we know about wavelengths of light? We know that there's a quantum of energy associated with each individual wavelength. So each element releases its own specific series of energies following excitation. So we have this violet light here. So if we think about for hydrogen, we have this violet light, which is, we know, a very high energy sort of visible light. And then a blue light, which is slightly less in energy. This sort of teal light, which is even lower in energy. And then sort of this reddish orange light here, which is a lower energy. So there are four specific photons of light, so four quantum energies, so four energies that are being emitted by the excitation of hydrogen. Whereas for helium, we don't see that high energy. We first see our blue, and then a lighter blue, then a green, yellow, and then two different reds here. There are 1, 2, 3, 4, 5, 6 individual energies of light that are released once we finish exciting helium, and so on and so on. So electron transitions. So line spectra are the result of electron transitions. So electron transitions are electrons moving from one allowed energy state to another. Okay, so we are going to get into, through the next few lectures, we're going to be understanding how electrons inhabit the atom. So first off, when we're talking about these energetics of an electron, we draw an energy diagram for an electron that's existing within an atom. So what we draw is we have a y-axis that we define with an arrow going up and an E, which stands for energy. So when we draw on this sort of schematic here, the lower we are on this graph, the lower in energy, the higher we are in the graph, the higher the energy. So if we have electrons that are located in a certain energy state that we call the ground state. And so this ground state, this electron that can hang out down here, can be at a lower energy level. When we insert energy into the system, so this could either be by burning a certain element or just adding in energy. In any way, you can excite this electron up to a higher excited state. We'll call this excited state A. Okay? So that amount of energy that we put in can allow that electron to be excited up to that energy state. If we add even more energy, say that we have a second excited state, called excited state B. If we add even more energy, we might be able to excite an electron up to excited state B. And so this process of increasing that energy state of an electron is called the excitation. And for excitation, we are adding energy into the atom. So once this electron is excited to one of these excited energy states, it wants to fall back down to its ground state, which is its lowest energy state. So all things want to be at lower energy. Okay? So think about you just living your daily life. Okay? Would you rather be running around getting tired or sitting on the couch watching TV? You know, it's fun to run around and everything, but it gets you tired out. Your natural state is to relax, to go to your lowest ground energy state. So these excited electrons that are up top here want to decay back down to its ground state. So an electron can either decay back down to a lower excited state, or the electron itself can decay back down to the ground state. And so these decay processes correspond to a specific energy transfer. Okay, so I'm going to erase a lot of this extra writing here so we can visualize this transition better. So again, we have our ground state, and we have our excited state A, our excited A, and our excited B. Okay, so we have an electron that has been, say, excited up to excited state B. So we can either have an energy transition from B down to A, or that electron can transfer down from excited state B all the way down to the ground state. Now there is an energy associated with each of these transitions, whether going from energy state B to energy state A, or going from energy state B all the way down to ground. Or for that matter, there's an energy associated with going from excited state A down to the ground. So each of these have a specific energy associated with it. Okay? And so this process of an electron returning down to a lower energy state is called emission. Okay? And so this emission is the electron dropping back down. And so the energy associated between the difference between this excited and ground state energy levels can be released as a photon of light. E is equal to h nu, or E is equal to hc over lambda. So what we get is individual colors of light associated with the transfer from an excited energy state down to a lower energy. So if we compare our three different energy transfers associated here, going from B to A, B down to ground, and A down to ground, if we were to list these guys in terms of the magnitude of the energy released, we would see that this transfer, going from B all the way down to ground, that is the largest energy gap. So that's going to have the highest, we'll call that number 1, our highest amount of energy released. Now if we compare transition from A down to ground, or B to A, which one of these is larger? You can see this transition here is larger, so that's going to be our second highest energy transfer. Now we take a look from B down to A, that's the smallest energy difference between the two, so that would be the third highest energy transfer. So if we're thinking about our visible lights that are going to be released, this transfer from B down to ground, that's going to be highest energy, so that's going to be more like violet. One going from A down to ground, it'll be more in the middle, so that's going to be something like green. I'm totally making these up right now, just sort of kind of illustrating how the energy works. And a smaller energy transition would be something more like red. Okay? As associated with our Planck's postulate, E is equal to h lambda. Okay, so the idea of different quantized energy for electrons corresponds to the Bohr model of the atom. So in 1913, the Danish physicist Niels Bohr proposed an atomic model as electrons circling the nucleus at specific distances in a series of concentric orbitals. And so the energy levels of the orbits are quantized. So the further you are out in an orbital, the larger the distance away, the higher the energy, and then the less negative E. Okay, so if we take a look, so this is the, so we'll put a drawing on the board here to sort of further illustrate this idea. So the Bohr model of the atom is the most stereotypical sort of drawing of an atom. So if you ask a layperson, you know, if your parents are not in science, if you tell them to draw an atom, they're most likely going to draw the Bohr model of the atom. And so where we have our nucleus here in the middle, so our nucleus in the middle, which is that dense core, and then you're going to have concentric circles that we call orbitals going out. And so these electrons are going to reside within these orbitals. Okay, we'll get into a lot more detail about this in later classes, but this is just sort of a justification here. And so the further away, the larger in distance that we get away from that center, the higher the energy that we have. Okay, so we know we have a bunch of positive charge here in the center, and with these electrons that are negative charge. So the further you get away from that center, the higher the energy of the orbital. So when we're talking about, so if we're thinking about our energy diagram going from a ground state to an excited state A or an excited state B, we're thinking about an electron that would be located on an outer layer decaying back down to an inner layer. So if we sort of erase these electrons that we have here, to understand what these transitions would actually look like, say we have an electron located on this inner energy level, and we'll call that the ground state. If we input energy, we can have enough energy to jump that electron up to an excited state. So that would be taking that electron, putting enough energy to excite him up. Then this electron could then decay back down to a lower excited state, or it could all the way decay back down to our ground state. And these are our emission events. And those are going to emit our light, E is equal to hc over lambda. Okay, so this Bohr model sort of justifies our drawing that we had for our justification for the line spectrum. So only specific orbits corresponding to specific energies are available to electrons. So you can't have an electron be promoted somewhere in between these two orbits. It can't be hanging out here in the middle. It has to go into the specific energy level orbitals. So because of that, these energy transitions are quantized. They're only going to be a specific allowed transitions with specific energy levels for each electron. So absorbing energy promotes an electron from a lower energy orbit to a higher energy orbit. So a larger diameter from the nucleus. And so the energy, these photons, are emitted as an electron falls back to the ground state. And so there's a fixed emission energy, E is equal to hc over lambda, of that transition. So this is just showing a slide of the drawing that I just drew on the board. So we are exciting an electron by putting in energy from a lower state to a higher state, and then as the electron falls back down, it emits out energy. And then each of those allowed transitions of those electrons moving will show up on our line spectra. Okay, so Johann Balmer and later on Johannes Rybar discovered a mathematical relationship describing each of the spectral lines in the atomic line spectra for hydrogen. And so they realized that when you excite hydrogen, you get these 4 individual lines. And they knew that each of those lines correspond to a specific energy. So they came up with this relationship. 1 over lambda, where lambda again is our wavelength, is equal to this Rydberg constant times 1 over m squared minus 1 over n squared, where m and n are both integers, and n has to be larger than m. Okay? And so later on we'll get to the reasoning of what m and n actually are. But they came up with this relationship that was really powerful and able to actually model each of these different transitions. Okay, so what do the m and n terms stand for in the Balmer-Rybar equation? All we know is that m and n are integers, and n is larger than m. Okay, so what do these mean? So the Bohr model states that the nucleus is surrounded by concentric circles of increasing energy. So if we draw our Bohr model, we have our nucleus in the middle, and we have energy level that we'll call n equals 1. Second energy level we'll call n equals 2. Third energy level we'll call n equals 3. And fourth energy level that we'll call n equals 4. Okay? An electron can be promoted by adding energy. Okay, so if we have this electron here in n equals 1, we can add energy in. So we add a photon of energy, and that electron can be promoted up. And we know that that emission back down can release an additional photon of energy. So here, if we convert this now to our energy diagram again, so instead of calling it ground state and then excited state A, excited state B, what we can do is assign those individual numerical numbers, 1, 2, 3, and 4. So we can call n equals 1 this ground state, and then a big jump up to n equals 2, and then a smaller jump to n equals 3, smaller jump to n equals 4, etc., etc. We can go n equals 5, and it keeps going. And the further out you get, the smaller and smaller the individual spaces, energy gaps between these different energy levels. Okay? And so these these n numbers, the m and n numbers in the Balmer-Rybar equation, talk about these electrons moving between these specific whole number integer energy levels. And so the definition in our equation, m, stands for the energy level where the electron ends. Okay? And n stands for the energy level where the electron begins. So n stands for energy level where the electron begins. So if we're looking at this transition here, we're not talking about the excitation when we're looking at a line spectra. We're only looking at the emission. So we can sort of delete this line going up. So if an electron starts in energy level 3 and decays back down to energy level 1, we would input in the Balmer-Rybar equation m, where the energy level where it ends would be 1, and n, where the energy level begins, would be 3. In this case, where we start where an electron in energy level 5 and it decays down to energy level 2, where it ends would be 2, where it starts would be 5. So these individual quantized energy levels associated with the Bohr model are actually the justification for this Balmer-Rybar equation. So changing m, the energy level where the electron ends, determines the type of emitted wave that we get. So if our m is a 1, so this is where the energy ends again. So we're talking about if this electron comes all the way back into the beginning bottom energy level, that means we're going to have energies associated with ultraviolet light. So this is the highest energy. So if we think about our energy level here, first shell, second shell, third shell, etc., any transition where our m term, so where the electron is going to end at the end of the electron transition, anything that's going to drop down to that first energy level is going to be in the UV range. Whereas anything that's going to come back down to the energy level 2, these are going to be in the visible wavelengths of light. Okay, so a smaller energy than these UV lights. And so the visible series of light, they call it the Balmer series. And then anything that returns to an energy level 3, that's going to be associated with an infrared radiation. So that's going to be even smaller. So if we ask the question, does this make sense energetically by looking at the energy diagram? Yes. We see our highest transitions are UV, our mid transitions are visible, and our smallest transitions are IR. So if we ask a problem here, which of the following electron transitions in the hydrogen atom will result in the light emission with the longest wavelength? So hint, use the diagram and think about the relationship between energy and lambda. Okay, so take a moment to think about this. Okay, so if we are thinking about finding an emission with the longest wavelength, so longest wavelength, so if E is equal to hc over lambda, if the longest wavelength means the largest number in the denominator, that means the smallest energy. So if we're looking at our different transitions, if we're talking about going from 1 to 3, that is an excitation, so that's not considered an emission. So A cannot be true. If we're going from 4 down to 2, that's going to be an emission of a moderate amount of energy, so that'll be a Balmer series, a visible amount of light because it's returning to 2. If we're going from 2 to 4, that's excitation, so that's not what we're talking about. If we go from 2 to 1, that's a much larger amount of energy than the 4 to 2. And so that's going to be a UV transition. And then if we're going from a 10, so it's about, highest up here down to 2, that's going to be another visible transition because we're returning back down to 2. So if we're thinking about which one is going to give our longest wavelength of light, that means which is going to be the smallest of the transitions, our correct answer is going to be B, because we have our smallest transition going from 4 down to 2. All right, so our next problem here is to calculate the Balmer series wavelengths for the hydrogen atom up to n equals 6 energy level and confirm these results with the line spectra. Okay. All right, so if we're taking a look at the Balmer series wavelengths, so Balmer series wavelengths mean that we are dealing with transitions that return back to the energy level 2. Okay, so if we have our energy level diagram, where we have our n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and then we'll, all the way at the top, n equals 6. So we're talking Balmer series, it's going to be returning back to n equals 2. So we're talking about transition from 3 to 2, 4 to 2, 5 to 2, and then from 6 to 2. So we need to do the Balmer-Rybar equation for each of these different transitions. Okay, so we'll set up the first one, and then to show you how to do the problem, and then we'll give you the answers for the rest of them. So the Balmer-Rybar equation states you go 1 over lambda is equal to our Rybar constant times 1 over m squared minus 1 over n squared. And remembering that m stands for the place that we are transitioning to, and n squared is where we're transitioning from. Okay, so we're going to solve now for 1 over lambda is going to be equal to our Rybar constant, which will be given to you, 1.097 times 10 to the negative 2 nanometers. So our first transition we're going to do is going from 3 to 2. So we are transitioning to energy level 2 squared minus transitioning from energy level 3 squared. So if we solve for this here, we're going to see that 1 over lambda is equal to, plug and chug here, 0.001524 reciprocal nanometers. So if we take that whole response and set it to the negative 1, so to take the inverse, we get an answer of 656 nanometers. Okay, so the other transitions, you're going to set up exactly the same way. And you're going to keep this m term as 2 for each one. And for the next one, you're going to swap it. Instead of coming from 3, you're going to come from 4. And then you're going to set up again coming from 5, and then set up again coming from 6. And so our final answers, when you plug and chug for these Balmer-Rybar equations, are going to be, so if we're going transition from 3 to 2, from 4 to 2, to 5 to 2, and then from 6 to 2, the answers here are going to equal, as we just solved, 656 nanometers, 486 nanometers, 434 nanometers, and then 410 nanometers. Okay, so now we want to take a look at the actual data that were provided to us on the line spectra and see if our results actually align. And we can see that our calculations match up exactly with the theory here, showing that the Balmer-Rybar equation is indeed valid for the hydrogen atom. All right, that's it for the day. Thank you.